Bert, it's an absolute honor to meet you. Can you introduce yourself?
Yeah, Tim, it's great to be here. Thanks a lot for the invitation. I'm a professor at Eindhoven University of Technology, which is located obviously in Eindhoven in the south of the Netherlands. Together with my students, we work on developing a toolbox for realizing active inference agents. When I first read about the differential principle, this is about 10 years ago, it was mostly about neuroscience and how variational free energy was the only ongoing process. So that was brilliant, but it was sort of in a way cast as information processing. Then a few years later, Carl started talking about this is really just the principle of least action applied to self-organizing systems, applied to information processing that must be going on in self-organizing systems, in biological systems, in brains, but even all self-organizing systems. More recently, this interpretation of a new branch of physics, I think, has been developing more strongly, and I think that's really exciting because now it has a very solid footing. It's a new branch of Lagrangian mechanics, which is the basics of physics in general. The principle of least action is centuries old, it's a very rich history. You can derive almost everything in physics from the principle of least action, so it has a very, very solid footing now. And it's so important. It will affect not only AI, but I think engineering and science everywhere, that at some point in the future, I think the differential principle will be taught in high school, in the natural sciences or the physics curriculum.
In the space of physical laws, the principle of least action gives us a parsimonious explanation for trajectories of systems, both simple and complex. Rooted in the calculus of variations, this principle asserts that the actual path taken by a system is one where the action integral, defined as the integral of the Lagrangian over time, is stationary. The Lagrangian, encapsulating the difference between kinetic and potential energy, serves as the cornerstone for this minimization process. At its core, it's an optimization process, a theme resonating deeply within all of the sciences. In a conceptual leap to cognitive science, Carl Friston's free energy principle mirrors this optimality, this idea that posits that biological systems, in their interaction with a dynamic and uncertain world, navigate by minimizing free energy, which represents a bound on the surprise incurred by their sensory states. This act of minimizing a scalar quantity to regulate and predict environmental exchanges parallels the principle of least action, illuminating broader principles that may underlie both physical and living systems. The elegance of least action guides our understanding of motion and change. In acknowledging the principle's relevance to Friston's free energy principle, we glimpse a unified view of nature's economy, a suggestion of a pervasive lawfulness that reaches from the celestial mechanics of orbiting planets all the way down to the intricate dance of neuronal activity.
The principle of least action is sort of an umbrella framework that says in nature, energy differences of any kind are minimized as fast as possible. So for big things that move about in the world, the difference between kinetic and potential energy are minimized. For charged particles that move about in electric and magnetic fields, the difference between electric and magnetic energy is minimized. If you do that minimization, so if you do that mathematically by finding the minimum of this action functional, you find the equations of motion. So in the case of electromagnetics, you find Maxwell's equations. In the case of classical mechanics, you find Newton's equations. And in the case of the free energy principle, you find update equations for information processing in brains and in other biological systems. basically what we do in our lab is to implement these equations of motions for information processing. This is just Bayesian information processing.
So like a military rucksack.
It is exactly that, right? Pretty much, and walk to work that way, because I have a 20-minute walk. It's like a farmer's walk, right? But it's fantastic for everything, for your core. I mean, if you walk with like, I don't know, like 30, 40 pounds on your back for 20 minutes.
I walk with 30 or 40 pounds on my stomach. Does that count? Does that mean
counts too? It does count, because I'm sure your legs are a lot stronger than my legs.
Yeah, probably.
Now, as many of you know, we've had Professor Friston on the show many, many times now. He is the ultimate gentleman. He's a huge inspiration to me. And I guess Professor Friston, more than anyone else, has really inspired Bert's research efforts going back about 10 years or so now.
So if you're saying that the superorganism is just drawing a Markov blanket around a particular culture or society or population or ensemble, or not set of conspecifics, I think you made a very clear point before that you cannot get a joint free energy minima just by looking at one kind of species. It has to be an ecosystem that necessarily has all sorts, even at one given scale, all sorts of different kinds of phenotypes within it. Things to eat, things that do the eating, things that do the breathing, and the things that you breathe. That scale-free perspective, and particularly the separation of temporal scales and scales that distinguish between an individual and the population or the ensemble in which that individual finds herself, is absolutely fundamental. And that certainly could be attributed sort of mental states of a minimal or basic sentience sort.
This is a really interesting vision where everything from individual cells to entire vast cultural systems are underpinned by the same fundamental rules. Friston paints a picture of an interconnected hierarchy where each layer, whether it's an organ, a body, or an entire society, is subject to the relentless discipline of the free energy principle, each encapsulated by the concept of a Markov blanket. Variational energy, often discussed in the context of the free energy principle, is a mathematical concept arising from probability theory, and it's at the core of how scientists believe our brains deal with an uncertain world. Now imagine you're in a bustling street market. There's a frenzy of sights and smells and sounds. Your brain is being bombarded with sensory information. Now, to make sense of this chaos, your brain is constantly making educated guesses about what's going on around you. It might deduce a sizzling sound as sausages cooking, or the aroma of coffee as a barista does their work. Now, these predictions are a bit like little bets that your brain places, and when sensory data matches these predictions, your brain gets to say, "Ah, I told you so." When the predictions don't match, your brain needs to pay up, figuratively speaking. It's like a debt. So variational energy represents the difference between what your brain predicts and what actually happens. When this variational energy is high, it means that there's a significant mismatch. Your brain is surprised, and it doesn't like surprises. Now, to minimize this surprise, which scientists quantifiably call prediction errors, how original, your brain adjusts its internal models of the world. Now, it involves tweaking and refining all of those little guesses to get a better handle on the barrage of sensory information. And this process is akin to a sculptor chiseling away on a block of marble with every single strike. The unnecessary bits fall off, and the intended figure slowly materializes into existence. Now, similarly, your brain is sculpting a model of the world where minimizing the variational energy chisels away the misinformation between predictions and reality, revealing a clearer picture of the world. Now, the key idea is to find a simpler distribution known as the variational distribution, which is close to the true complex distribution that we're interested in. And by close, I mean that the variational distribution minimizes a certain divergence measure from the true distribution, which in this case is the KL divergence. In essence, these methods transform a difficult problem into a more manageable one by finding the best approximation within a specific family of distributions. Now, while exact solutions are often unattainable, variational methods grant us the next best thing, an approximation that lets us make structured inferences about the state of the world or the underlying process being studied.
I think the last word on the relationship between information and physics hasn't been said yet, right? But if I look at the variational free energy, and it allows a decomposition in what's called a complexity term minus accuracy term. The complexity term measures how much your beliefs are moving. So you can interpret this as a kinetic energy of information processing. The accuracy term tells you something about how much do I know about something else. This is the potential energy. So there even also for the free energy principle, you can kind of see this that it's trying to minimize the difference between energies, if you will.
Yes. But maybe just to linger on this a tiny bit, what do you think is the relationship between entropy and information?
In information theory, you can interpret it as a generalization of the variance of a Gaussian distribution. There are many other distributions. They don't have to have one peak, but they can have multiple peaks. And if you want to express in one value how widespread, how spread is this function, is this distribution, then entropy is your measure. Now there are much better derivations for it, but this is a way of how it measures the spread of a probability distribution. Then of course there's a whole physical interpretation about that it's the uncertainty that you have about the microstates in a physical system when you can only measure microstates. There is an interpretation that I like very much in information processing, and this is by Ariel Katica, and he posed the question, so let's say I have a probability distribution over a set of variables, and we know that the only rules for manipulating these probability distributions are sum and product rules. That's what probability theory is about. But now I inject information. I want to inject information, get information from a site into that distribution. How should I process that? If that new information is an observation, you can use a likelihood function and use Bayes' rule. But sometimes new information is not an observation. Sometimes it's just a constraint on the probabilities. I want to be in the temperature of my body must be around 36 degrees centigrade, but not exactly. So there is a probability distribution. This is new information, I want to incorporate that. And he shows, or actually it goes back to an article in 1980 by Shore and Johnson, that the proper way to update your probability distribution with new information is to incorporate the information and then choose the maximum entropy distribution. So the most uninformative distribution while accepting the new constraints. This is the same thing as saying we're going to do variational free energy minimization subject to the constraints. In other words, variational free energy minimization is really the optimal way of processing information. And so in that sense we're doing the right thing, right?
So we're doing probabilistic inference. We have these probabilistic graphical models, and the problem is these normalized distributions that we want to compute are intractable. The domain is exponentially large. So how do we do this? Well, you probably know about Markov chain Monte Carlo, especially if you've watched the introduction to our Bengio show. Now, that's a great way of getting an optimal solution to modeling these normalized distributions, but unfortunately it can take exponential time to run, right? We don't have all the time in the world. So another thing that we can do is a family of methods called variational inference. Now, essentially, the idea is that you cast inference as an optimization problem. The first thing you do is you create a low-resolution approximation of the distribution that you want to match. And then you have an optimization problem that kind of tweaks the knobs and the levers on that distribution until it fits as closely as possible to the distribution you want to match. There's a real engineering challenge implementing the free energy principle. So when we speak with Friston, we talk about this beautiful principle that is quite abstract and can be applied at many scales. And when we talk about the engineering reality, we're actually building these models that do variational inference.
Yep.
And we have this explosion of computational complexity, and we have to do a whole bunch of handcrafting, and it's not quite as some of the purity kind of melts away, I guess. What are the biggest problems that you're trying to overcome?
So far, the discussion has mostly been, how can you get away with not doing cost functions? How can you get away with not doing control? Right? How can you get away with just doing prediction and updating and error correction? It never has been so far about how to implement it. So let's say I want to build an active inference agent for autonomous driving for a car. And so my car is driving on the road and I see another car is coming at me, so I need to avoid that car. That means I have to apply a Kalman filter to that, to the path of that car, and also a Kalman filter to the path of my own car. And that means that if these Kalman filters consume 5 watts, I have to spend 10 watts. So as I get closer to that car, I see there's suddenly a cyclist on the road. I need to avoid that cyclist as well. And I have a look in my rear view mirror and I see there's another car homing in at me. I need to also keep track of that car because I cannot brake very hard. Now I have to run 4 Kalman filters, and with a budget of 10 watts, I only have 2.5 watts for each Kalman filter. So I have to keep shifting the power budget to each Kalman filter. And you can imagine in a world that keeps changing, I have to actually have available Kalman filters that run on 1 watt and on 1.1 watts and 1.2 watts and so forth for a whole range of latencies as well. I cannot program all of that in my system, and that means I have to have a different programming strategy. I have to have a reactive programming strategy. I just have to let it happen. I must be able to apply 2 watts to my Kalman filter and 1 watt. If I apply 1 watt, it won't be as accurate, but I still want a Kalman filter. I still want it to run. And that's one of the difficulties of implementing reinforcement learning with active inference. I think that active inference actually has a chance of being implemented in this way. So in the way of these fluctuating resources. And I think it's much harder to do that for let's say, competitors of active inference like reinforcement learning.
This is Jason Fox, the Chief Technology Officer at Versys.
No, you're right. I mean, we're as engineers, just like in general, I think we're used to deterministic systems, right? And machine learning AI introduces a lot of non-determinist outputs that you have to learn how to deal with and adapt to. And specifically, large language models are probably one of the most non-deterministic machines that I've ever had to interface with.
This is Riddhi Jain Pitliya, a researcher at Oxford University working on active inference.
Oh gosh, how does that work? If I had the answer to that, we wouldn't be over here with a team of researchers. I wish I had the answer to that. No, we're still working on that. We're still developing it. We're trying to scale it up in a very manageable, practical manner that is still very, very principled. I think that is just, Carl does an excellent job of just keeping us grounded to make sure that everything is done in a principled manner. So then we really get the emergent properties from the propositions of the model. And in that hope, I'm hoping we can form some form of a digital version of intelligence as captured by our reality of intelligence that exists all around us, like non-human intelligence as well, right?
You were working in a similar industry to me, my startup, X-Ray. You were doing signal processing for hearing aids, and you were just speaking before we hit the record button about this agential view. So active inference, in a sense, is about seeing the world or modeling the world with agents. And you were saying how you could model a hearing aid as being an agent.
Actually, I'm still working on hearing aids.
Oh, sorry.
in my research projects, and I'm also still affiliated with a hearing aid company for a day per week. So a hearing aid is well, we know what a hearing aid is. It's a small device that processes an audio signal. It's designed by a hearing aid manufacturer, by engineers on their desks, and it has an algorithm with lots of parameters. You go as a client to a dispenser. The dispenser plugs in good values for your parameters, and you're very happy, and then you leave. Everything is fine until a few weeks later, when you are at a restaurant and you cannot understand your conversation partner. There's nothing you can do. The designers of this algorithm, they're not there. The engineer and the audiologist are not with you. So you have a problem. What I would like to do is to make the hearing aid itself a self-organizing agent that is responsible for keeping the patient in a satisfactory state with respect to the acoustics, right? Meaning that if the hearing aid now is an agent that tries to estimate what is the state of the client, and if it's not happy, it tries to explore actions by setting parameter values to different values. Tries to explore actions so as to make the patient happy again. Actions by changing parameters in a hearing aid algorithm will of course change the processing and will change the sound signal that the client will hear. So that would mean that the designer who is responsible for designing the hearing aid now moves from people that are professionals at their desks to the hearing aid itself under in-situ circumstances. And I think it has a tremendous advantage if you can solve problems with your hearing aid in the field as they occur.
Yeah, and I think this is such an instructive example, because we speak about natural intelligence. So we're moving away from something which is statically programmed, and at X-Ray we see this all the time. So different handsets do different types of audio processing, and I have to look at the spectrogram, and some of them do voice isolation, some of them do dynamics processing, and they're making assumptions about what works best in all situations, or even sometimes they do some personalization. It's still just really old school, right? What we need is an agent that can make intelligent decisions based on the environment that they're currently in. But it leads to the question, though, of, I guess, alignment, because we're talking now about growing an AI rather than designing an AI. And we now need to gently pressure it to do the right thing in the right situation. How would we do that?
Okay, yeah, this is a problem. We actually get, I think, to the difference between reinforcement learning and active inference. And there is a big difference in philosophy, right? In reinforcement learning, comes from psychology, then made quantitative by people like Andrew Bartow and Rich Sutton, and it's a beautiful theory. But in active inference, we say the entire process is variational free energy minimization. So there is a conceptual big difference. In reinforcement learning, the idea is there are valuable states in the future. A patient that's happy is a valuable state. So I want to measure that by having a value function over those states. And the idea is for the hearing aid now to take actions to fulfill or to maximize the expected value. So that's fine if the world doesn't change, because that value function is a proxy, is a reflection of your problem statement. Maximizing that value function is your solution proposal. So where's the problem? Well, it's contained in that value function. Now, if the world changes, or if a situation occurs that you didn't test for, that you didn't, like going into a restaurant and the cluttering of utensils is very annoying. You didn't test for that. So there's a new situation. Then reinforcement learning cannot deal with that because it cannot adapt the problem statement, the value function. So in active inference, the function is a variational free energy. The variational free energy decomposes into two terms. One is minus the logarithm of the probability of the data. It scores Bayesian evidence. It scores how well does the model represent the world, how well does my model predict the world. It's your problem representation costs, plus a so-called Kullback-Leibler divergence between the variational posterior and the Bayesian posterior. You can think of that as your solution costs. In active inference, everything, the entire process is inference, so the solution is obtained by inference. And so now you have a cost function that underneath has problem costs plus solution costs. If the world changes in active inference, the problem cost will go up, and free energy minimization over the structure of the model will happen if that's built in your, if you have a toolbox for that. And so then your model will keep following the world, and in that way do a lot better job on the alignment problem, because it can follow the world.
Could we just clarify for the audience, because as you say, reinforcement learning, we have this concept of a value function or an advantage function, and we have a reward, and the reward is handcrafted. It's usually quite brittle and hacky, but it's domain specific and it's intelligible. You know, there's going to be alignment problems, of course, but in the free energy principle, it's far more principled than that. So we're just minimizing Bayesian surprise, essentially, and the machinations of that you were just talking about. There's this KL divergence, which is like, you know, how much should we penalize based on the difference between these probability distributions? But I guess I'm saying that that's fidelity. It's not really a pressure to do a particular thing. And then on the top, we could move towards goal-based learning, and we can kind of say, okay, well, I'm now going to apply specific pressures to meet certain goals. So could you contrast that with value-based learning and just,
so in the free energy or in an active inference process, all that happens is you have a model, a generative model of the world. That model makes predictions of sensory observations that is matched by the sensory observations. You have predictions errors, and these prediction errors are processed. And there is a little twist, namely that we are allowed to set constraints on that generative model, which makes that generative model not just a model of the world as it is, but more of a model of as we want the world to be in the future. So when we roll out this biased generative model, we're going to have a representation of where we want states to be. In the case of a hearing aid, one of the states could be the estimated satisfaction level of the patient. I could clamp that to satisfactory values, to values that we say, okay, this represents a satisfied patient. So now, if I do now variational free energy minimization, then all the actions will be inferred, both explorative and exploitative, to fulfill that future state, to fulfill the promise that the patient is going to be happy.
Okay, on that though, there's ambiguous trajectories. So if a goal is a future state, you can get there in many different ways. sometimes you might not be enacting it, you might be imagining it, and the representation might be quite brittle because it depends on the underlying factor model structure, your Bayesian model and so on. So does that introduce any form of brittleness or problems from an engineering point of view?
Yeah, I mean, let's say the path that will be taken is a resource conserving path. Actions will be taken to elicit information to resolve the uncertainty. So it's data preserving. We want smart data. It's also power conserving, because this complexity term in the free energy is the movement of the beliefs, and it relates to how much power. If I move my beliefs, I need to consume power. So how much power is to be consumed. The path that will be taken is the path that consumes the least amount of resources. You will always have in the free energy principle a trade-off between accuracy, the goal that you want to achieve, and how much resources you will consume. In active inference, you will never build a perfect model. You will build a just good enough problem representation and just good enough solution for that problem. It doesn't help you to have a fantastic problem representation and not being able to do inference in that model. Mm-hmm. It doesn't help you to have a very poor problem representation and do perfect inference in that model, because then you solve the wrong problem. So active inference will give you just a good enough solution for minimal resources. That's the path that will be taken.
This is Stephen Swanson, the Chief Administration Officer at Versys.
Well, there's this thing called black swan phenomenon, where the three criteria. One is it has a huge impact. Number two, it couldn't have been predicted. But number three, in hindsight, it was obvious. And so, microwave would be probably an example. Computing, vehicles, any number of really big, impactful technologies or inventions. In hindsight, they're kind of like, of course, someone could have invented that. And in this case, I think the notions of interoperability and governance and agent-based systems, it will be, in hindsight, obvious. I think there's an audacity that underlies it, where because the wicked problem in computing is that in the very beginning of digitalization and computing, every company, every app software developer took these ingredients, took these recipes, these software code and data structures, and kind of reinvented the wheel on their own. And so you end up with this Tower of Babel, where everyone's got their own, unique combination of those ingredients, and the interoperability and the connections between them is very fragile and delicate and very bespoke to get them to work, and it's kind of janky. And so this idea of like, well, what if we started from not scratch, but we started from a universal baseline that not everyone has to drop what they're doing and adopt, but build connectors to it so that there is a bit of a Rosetta Stone, not just from a communication standpoint, but from a data structure standpoint. The idea is simple, and again, I think obvious in hindsight, but kind of profound in its implications.
Yeah, but I don't know that correspondence. I don't know about quantum mechanics. And,
not many do. We interviewed Stephen Wolfram, and he's got this book out about the second law of thermodynamics, and of course he thinks it's all the Rouliad, which is interesting. But quantum stuff emerges from that. But I guess what struck me is just how many fundamental things like that are still theorized by physicists.
Yeah.
Whereas if it's a camera like that, then it's like, I'm on camera. So there's so much I want to say, but I want to save it. I want to save it for when we record.
All right. Okay.
I don't want to lose any potential material.
I really enjoyed your presentation that you recorded for this Active Inference Institute.
Thank you.
Yeah,
appreciate that.
Because that is kind of what we're doing. We're building a toolbox for free energy minimization, and we don't follow the actor model, but from what I read about it after you talked about it, it's quite similar, right? Our factors are autonomous systems that just decide for themselves when to fire and what to fire, and there's no guiding umbrella algorithm really. It's just a reactive system.
Yeah, what's interesting about the actor model, and Tim and I and the guy who works with us at X-Ray, we talked about this quite a bit over the last few months, is because of the kind of current state really of programming languages, it turns out that the most usage I've gotten out of the actor model is really applying its principles or subsets of its principles to, throughout the code. It's kind of like, okay, I go and write a class. Maybe I'm writing a function, for example, and I'll use actor model principles when I design that function. So, for example, early on, we settled on the fact that the best way for us to communicate between threads is through concurrent queues. Like you just have these queues and you pass information, right? And if you do it that way, if you're pretty strict about having all communication essentially being through these message, pipelines, it saves you so much headaches with trying to debug multi-threading problems. Like essentially you just, you've isolated the compute. You don't have shared state where they're sitting there overwriting each other.
Right.
And so principles like that are so useful.
It's the ultimate divide and conquer strategy, right?
Yeah. I mean, Bert, thank you so much for joining us today. I'm really looking forward to our conversation.
Yeah, so am I. I mean, thanks so much for inviting me. Really a pleasure.
One reason I'm really looking forward to it, and it's something you said in the email you sent over to us. You said, "Hey, look, guys, I'm not a philosopher. I'm an engineer, right?" And I appreciate that so much because while Tim and I do this show, which does oftentimes meander off into philosophy, it's not our day job. Our day job is we're engineers. We're software engineers, and so our bread and butter and what we do for way more hours than we probably should, almost every day of the week is engineering. And I mean, you would agree with that, right, Tim?
Absolutely. Yeah.
Yeah. And what I find interesting about engineering is because it's not an open-ended research effort, you're trying to solve problems on deadlines, right? It's like, you got to get this solved in 6 months or 1 month or 6 days, right? And that crucible really forces you to find solutions to problems. And you don't care whether they're theoretically pure or, anything like that. You're looking for things that work. And what I've found, my personal experience has been that when I was put in that crucible, it forced me to, sometimes without even me knowing that these were paradigms that even existed until later, to discover, among other things, Bayesian methods, the relational data model, the actor model of compute, and I think for some people, active inference, falls into the same category of things. Has that been your experience too, that just the crucible of needing to solve difficult real-world problems is what's pushed you into these domains?
Yeah, absolutely. In my case, I mean, by the way, the active inference community is still so small that I think almost everybody who is doing research or development in active inference has an interesting story where they came from. And in my case, I was just a researcher in the hearing aid field. I was doing digital signal processing for hearing aids. And the issue with hearing aids is that the designers of the hearing aids are, namely the engineer and the audiologist, they aren't there when the problem occurs in the field with a hearing aid patient who cannot understand her conversation partner or whatever the problem is, cluttering utensils. And so I was just browsing the internet during Christmas, reading random papers, and I happened to read, and this was, I still remember, it was 2013, with Christmas, I happened to read a paper, A Rough Guide to the Brain by Carl Friston, that I never heard of, Carl Friston. But it resonated with me because it was talking about Bayesian inference, variational Bayesian inference, and I had been interested in that kind of stuff. And it hit upon me that because of the wording in that paper, that, hey, if we would use this theory that I didn't understand, but perhaps we could use this theory to make the hearing aid itself be responsible for its success and for taking control in the field when problems occur in how to solve it. Let the hearing aid take the initiative to design the trials and that kind of thing. So, I think this idea of, because there is a pressure to solve things, that as an engineer you read papers with a certain purpose, right? I read papers then, sort of browsing, but always being alert that it might be interesting for solving the problems that I have. Right. I also find that, I've been for a very long time, more than 20 years, purely in industry. And then only very recently, a few years ago, I went to academia. That the main difference is in academia, it's almost enough if a problem is interesting. And in industry, it must be interesting. If you're a researcher, you don't want to work on not interesting problems, but it must also be important, right? So you have to have that second criterion of that it has to be important. And that's also always in the back of my mind when I read a paper, right? I mean, what's the relevance of it, aside from whether it's interesting or not? How can we use it?
Yeah, and I almost find it's almost a magical moment when, you're an engineer, you're trying to solve some problem, you start to arrive at a solution, and maybe you've got a partial bit of solution, and then you happen to chance upon a paper that introduces you to an entire set of concepts and studies that you didn't even know the name of, like, for example, the actor model. And you're like, oh my God, this is great. There's a whole bunch of people that have worked on this problem and have tried to solve it. And Tim, I know you and I had a very similar experience with the actor model, and you even wrote some libraries, years ago at Microsoft. Like, tell me about what drove you to that framework and data flow, and what it felt like when you figured out this was a thing.
I mean, when I was at Microsoft, we were doing lots of deep learning projects, and it was a different deep learning project almost on a month-by-month basis. But we needed a streaming architecture. So we came at it from the point of view of streaming, and we were using Python, and I think there was a library called Pipe by Julian Pallard, if I remember his name correctly, which allowed you to do something not too dissimilar to LINQ, integrated language query in C#. And we essentially just overloaded that so that you could pass around streams of Python dictionaries, which represented mini batches in deep learning training. And we just kind of built this whole framework around it. But streaming is an important component of active frameworks.
Yeah,
absolutely. I mean, this, it's so funny how this idea of message passing between autonomous actors, agents, things, in the most general case, whatever you want to say it, just this simple message passing is such a powerful mechanism, right, Bert? I mean, we're going to get into this a bit more later, but I mean, you've done some tremendous work on just how much you can get away with this simple mechanism of message passing, and we'll talk about it more later. But just in general, isn't it a bit strange that such a simple mechanism, a Markov boundary, and messages going across them comes with so much capability?
Absolutely. And so I think, if you have a non-trivial model, so a model that has a large number of variables, and you need to do inference in that model, you must factorize. And you must say, okay, I have just these modules. I'm going to have a modular approach, but I must have modules, and each module depends just on a subset of variables. And then these modules communicate with each other. So in probability notation, that's just you have factors. You can draw a graph or factor graph. It's just a visualization. If you do now inference in that graph, you have message passing. So in practice, to me, any bigger model, if you really want to do a Bayesian inference, you are already doing message passing. You don't get around it. It's just that when the problem scales up, nothing else will do, right? You want to take advantage of the independencies, and message passing does that through the distributive law, but I mean it does it in a let's say in a transparent way. You don't have to do anything about it. And so I think message passing is the way to do Bayesian inference in almost any non-standard setting, or let's say non-trivial setting.
Yeah, and I think it's worth us kind of diving in a bit for the listeners on what this fundamental problem is we're trying to solve and why it's so difficult. And so my perspective is that it's clear really if you study it much. Okay, if you study probability theory much, that Bayesian methods are the one true, they're just the one true mathematical analysis method, for these kind of probabilistic situations. The problem is when you try to apply it, you get confronted rather quickly as soon as you get into any interesting model or a large enough model with these massive integrals, okay, that you have to perform. And sometimes are related, for example, to marginalization. Folks out there have heard that. But basically, it's saying to you, hey, look, here's how you solve the problem. It's this massive multidimensional integral. And that's just not something that we can do computationally. And so you have to find shortcuts. You have to find heuristics. You have to find tools that allow you to do an approximate, solution to this very, very difficult problem efficiently. And that's really at the heart of what you're talking about, right?
Yes, absolutely. Just to as a bit of a side remark, because you mentioned the term marginalization, I read the other day something Michael Jordan wrote. I mean the Michael Jordan from Berkeley, not the basketball player.
Yes.
And so he said, well, if you build complex systems, there are two very important concepts. One is modularity, and the other is abstraction. And it's exactly those two concepts that are very nicely captured in probability theory, namely modularity by factorization and abstraction by marginalization. And so this is one of the reasons why probabilistic reasoning works so well in complex systems. But I mean, and then there is, of course, you can even prove, going back all the way to Richard Cox in, I think, 1948 or around the 40s, that if you want to design a calculus for dealing with uncertainty, and you assume a few basic axioms like if I believe more in A than in B, and I believe more in B than in C, then my calculus must derive or must infer that I believe more in A than in C. Otherwise, it's just not logical. With a few of those assumptions that we all agree on, probability calculus turns out to be the unique calculus for calculating with uncertainty, right? It is the natural extension to logic, to Boolean logic. There is a now in terms of implementing it, you talk about integrals, and so in practice the proper way is indeed free energy minimization. There is something very nice about message passing that a lot of people don't realize, and that is that, in active inference, we just need to minimize free energy. That's the only thing we need to do. But if you go out in the world, if an agent goes out in the world, it's interrupted all the time because there's new things happening that were not expected. There's suddenly, if you're in traffic, suddenly there's a car coming from behind you or whatever, and you have to, whatever you were doing, you have to get interrupted. if you implement free energy minimization by message passing, then every time two messages collide on the graph, you do a little bit of free energy minimization. You carve away a little bit of free energy, and you can do thousands of messages per millisecond in a reasonable computer. And that means that you can interrupt at any time, because if the only process is free energy minimization, and we can do free energy minimization consists of sort of a nested free energy minimization by passing messages that only live for a millisecond or even shorter, then we can scale the amount of computation we do for our Kalman filters. We can run Kalman filters on 300 messages per millisecond, but also Kalman filters on 100 milliseconds. And we can stop a Kalman filter short after 50 messages and just read out the state and say, well, this is the best we have at this moment. And that's what we need when we have situated in agents, when we go into the field. And I think so it's no surprise that the brain sort of is doing kind of a reactive message passing kind of thing, right? Because the brain gets interrupted all the time. At least the processes in the brain get interrupted all the time.
Yeah, and I'd like to dive a bit, and this is a favorite topic of Tim's, so I'd like to pull him in here too, which is really the situated, it's the situated case, right? I.e., an agent who's not in some abstracted, theoretical, pure state, but more like it's in a world, it's interacting with other agents, with the environment. It's almost necessary that it has to be able to have this type of autonomy where it can handle interruptions, it can interrupt the process itself. I mean, am I spinning that correctly, Tim? Because I know this is something that you think a lot about.
Yeah, I mean, we were speaking about this a bit outside. I mean, first of all, I think one component of the situated hypothesis is that cognitive processes are largely externalized outside of the body. And you were just saying something interesting as well about the relationship between autonomy and being situated. Can you expand a little bit on that?
Yeah, well, I think if I'm situated in an environment and all these unknown, factors are kind of impacting me, or at least I'm receiving, information from essentially an unknown environment, it seems almost necessary. And I guess actually thinking about it's baked into the free energy principle, which is I need to be able to adapt. I need to be able to have this autonomy to evaluate now and adapt to the new information that I have. Whereas if I have less autonomy and I'm just kind of set on a particular course, well, then I'm just going to crash into the wall. Like if I'm a self-driving vehicle or something. Like, is that, I mean, Bert, it sounds to me like that's at least part of kind of the necessary condition that you're talking about.
Yeah. I mean, that's up to, let's say, up as far as I know, all factor graph. I mean, we just talked about why we need to have a factor graph, why we need to have message passing.
Right.
But as far as I know, all existing toolboxes for message passing come with a pre-schedule or with a message passing schedule. So you factorize your model, and then before you actually execute your process, you say, first I pass message 1 going from this node to this node, and then I pass this message, and then this message, and then this message. Now, if you are in the field and there's a cyclist, you have to track that cyclist all of a sudden. Basically, that's a model extension. You have to start up a new Kalman filter. You would have to reset your message passing schedule and schedule again. And indeed, you will just fly into a wall because free energy minimization is the only ongoing thing. So if you're not doing that, then you're doing nothing. And you will just fly into a wall. So we have to have an autonomous system. There cannot be some pre-scheduled message passing schedule, right? It has to just react to the circumstances. And I think that's, you see that in the actor model, and we call that reactive programming. But it's the same thing. It has to be reactive.
One thing we were touching on in the woods was the limits of autonomy and the limits of continual learning. So when an agent develops maturity, there's this kind of monotonic increase in behavioral complexity. So essentially the model it learns is a little bit like a simulacrum or a map of the environment around it. So it learns a map, and you could argue that the bias increases, the variance decreases. So this agent now has less autonomy because the only things it can do are the things it knows. But that does kind of imply that agents lose flexibility with maturity and therefore lose autonomy.
Yeah, I am not. I can follow the argument, but I'm not sure if there aren't any shortcuts in the argument, right? Yeah. So what we also talked a bit about that. How I like to think about this is, from what I understood from a paper by Rosalind Moran, is that as we grow older, so lifelong learning, and for older people, they're going to encounter less data in the world that they haven't seen before. So there's going to be less, let's say, model building on and working on accuracy. But we will keep working on that complexity term in the free energy, and so our models will become simpler and simpler, and therefore will generalize a bit more. We are becoming from specialists more like generalists. We are able to connect issues and topics together because our models become simpler, which is still a matter of, I mean, it is in line, it aligns with free energy minimization. You just minimize your complexity, but you're not going to see a lot of data that's completely new. That's and I don't know if that aligns with saying you become more stuck in a rut, right?
Well, it feels like that's not the case. I mean, it's a really principled thing to do. Many types of model training have a kind of complexity cost in there to create this. You basically just when you reduce the complexity, the idea is that you generalize more because you're not overfitting to all of the micro details. So if that is something that happens over time, that seems to imply to me that the model maintains its flexibility.
Well, let me interject here, because I think what you're both saying actually is right, and I think what we need to inject into this conversation is that if you think about evolution, right, it doesn't operate on the individual. It operates on the species, which is essentially, in the context that we've just been talking about here, it's really the model generator that it kind of acts on. So a particular instantiation of a model, you, me, an actor, right, a particular training of GPT, whatever it is, I think it does kind of crystallize over time. Like it reaches a certain, so look, this is what I've learned about the world. It's been working because I'm still alive. I've survived, and I'm going to stick with this until basically I die, like until I find out my model's wrong. Okay. But the thing is, there's other individuals that have other models, and they've had a slightly different, trajectory, experience, set of knowledge, and they've crystallized in different ways. Right. And so natural selection sort of whittles out the good from the bad. Right. Like it seems like on an individual basis, Tim, I think what you're saying is absolutely true. I think on like a species or a model generation basis, I think what Bert is saying can apply as well, right? Which is that you can transfer information between individuals and as a whole continue to develop, new models.
Yeah. I mean, I think in a sense we are the trials of natural selection, right? Each person individually is a trial.
Training trials.
Yeah, like that Black Mirror episode.
That's right.
Well, let me pull in another aspect that I realized when you were talking about. We continue to work on the complexity term. We continue to compress and find simpler models, simpler abstractions that capture the world model, that capture the world that we live in. What I find really intriguing about that is language is also a form of compression. And most people look at that as a bad thing. Like it's like, oh, language sucks because it's compressed. I can't just directly transfer my pure thoughts and all their complex nitty-gritty form over to you. It's really a shame that I have to, compress things down into this junky, like ambiguous language and send it to you. But on the other hand, that has a positive effect because it forces simplification. It forces reduction in complexity. So if you think about these individuals, they spend a lifetime learning, trying, testing, improving their models, simplifying. Now they need to communicate it to other individuals. It's almost a good thing that it has to be compressed and simplified to communicate, right? Because in the end, that's the goal, which is to find the simplest models that work really well.
Could I push back on
that? Or yeah, Tim.
Well, I just wanted to push back on this idea that language is a form of compression. I kind of I love this way of thinking that we have these rich generative models, and we use language to condition others. So your generative model is conditioned by the fact that I use a certain word. So the information isn't enclosed in that word. It's just a conditioning force. So I think of compression as being, I'm somehow taking all of the information and I'm, encapsulating it inside something, whereas language seems more like a code book.
Well, I think I don't disagree that it's a code book, but I think when we go to communicate a new abstraction, if you will, a new model, we're taking all these codes and we're combining them, and these codes are limited in their fidelity, right? Like if I say to you, a pile of sand, like I'm not communicating all the details of the sand. I'm communicating this abstraction of a pile of sand. And so I think when we build up these new models with all these abstracted components that are approximate, that's kind of the compression I'm talking about. And it's like what we struggle with. If I have some complex concept, right? You told me this one day, Tim. You said, I'm not very good at explaining what's in my head, to other people. And
I think there's also...
that's true.
There's also in language this idea that there's a digitization in it, right? So there's a noise reduction in the same way that with digital communication, it's useful to know that either a 0 or a 1 is being sent, because if I receive 0.8, I'm going to round it to 1. And in the same way, if we just categorize things in this is a house and that's a car, and I would send you a message that is like, well, if it's only going to be a house or a car, but it's closer to a car, you're just going to round it to a car. So you do a lot of error correction in communicating languages, right? And we have similar models about the language, and by communicating in a digital way, you can become quite robust to disturbances.
Yeah, and that's a beautiful segue actually to something I wanted to pick your brain on a bit more, which is you made this connection from marginalization to abstraction. And obviously marginalization is a coarse graining, but can you dive into a bit more? I mean, why can we view abstraction as marginalization? What's the connection there? It seems quite interesting.
Marginalization that leads to abstraction because you factor out variables that provide more details, right? This is a way of, not every marginalization is an abstraction, but if you marginalize out, let's say, the details out of your model, then you're left with a low-pass filter. You've basically done a low-pass filter, but not like a regular low-pass filter over time, but just over concepts. So and over your variable space, and so I think that so marginalization is needed to bring about hierarchical levels of abstraction.
Okay, and I think, help me understand something that is intriguing me here, which is in the old days, back when I used to do a lot more Bayesian analysis, I always had the model to start with because, I did some physics or some biological modeling, and so I had a model. And I also already had an idea of the variables that I cared about and those that I didn't. And so for me, marginalization wasn't introducing a new abstraction. I already had the abstraction. Is it possible to discover new abstractions by instead inverting that process, where I'm looking at variables and figuring out these are introducing like fine-grained detail that aren't important for solving some problem, and in some kind of like automatic sense figuring out that they can be marginalized, which then leads to an abstraction?
Yeah, so this is one of the advantages of let's say doing a variational Bayesian or a differential minimization in a factor graph. In a factor graph,
okay.
In a factor, your probability distribution is just a product of factors, and each factor just basically fends for itself, and it sends out messages and receives messages. These sending out messages are, and you talked about that as well, are the actions, and the receiving of messages are the sensory inputs. Now, at the back end of every model, you have to set some values to parameters, your hyperparameters, right?
Sure.
And so these hyperparameters can be seen, or the values can be seen as a vector that's sending out a message saying this is the value of this parameter. They will get back from the graph a message which is going to be interpreted as what the graph thinks about that variable. And there could be a prediction error. You could see a hyperparameter just sending out a value as its action. I think this parameter should be this value. And the graph sends back, no, I think it should be this value. If that persists over time, you have a good reason to say, I need to extend my model here at the back end. And so this is a way to create higher levels of abstraction, or to extend your model from the back end.
That's really interesting, and I think so for our listeners, and we'll also have probably some diagrams on the video. But I think if you can just imagine a graph, right, and you've got all these nodes and arrows come in and arrows come out of nodes, and I think if I have an arrow coming into me, then I'm a child of the parent, that's sending me this arrow in. And you said something really interesting there, and it's the heart of this curious asymmetry in these variational algorithms on Bayesian graphs, right? Which is that if I'm sending something to a downstream component, I know my parameters, which, and let's just assume for a moment they're a set of moments, the mean, the variance, maybe some higher order moments. So I know those parameters. And so I'm sending those down and I'm saying, this is what I think, my model should be. And yet you said something really cool there, and it's the asymmetry, which is the graph, your children and all the parents of your children are sending back to you kind of a collective information that's saying, hey, glad you think that that's the way it should be. This is the way we think it should be. And it's really the difference between those that is the heart of the optimization algorithm that's kind of occurring in real time on this graph. Is that right?
Yes. I mean, so any probability distribution, if you factorize it, you can draw a graph. Now you can pull, in a vector graph, a variable is associated with the edge, and all the let's say the probability distributions are in the nodes. So if you pull your graph up by the edge of your variable, and then you have sort of two trees hanging down from that edge, the left side thinks something about what that value should be for that variable, and it will send a message toward that edge, and it integrates out, or it marginalizes over all the internal variables of that graph, and it says, this is the probability distribution. I think this variable, this is my belief in this variable. You can think of that as a prior. It's a prediction. Then the other end of the graph, it may be connected to the world, and it may have sensors, and will marginalize over all the internal variables in that subgraph and sends back a message and say, well, the world, the sensory information I got and then, processed through my graph says this is the belief I think about this variable. And the multiplication of these two messages is nothing but Bayes' rule. It's just a prior times a likelihood. So you're doing a distributed Bayesian computation in a vector graph. It's completely distributed Bayesian computations. Every node, or every node just fends for itself, but every variable gets a prior and a likelihood, or if you will, a prediction and a correction, right?
Right.
So yeah, that's a very good, nice interpretation. If you do that at the edges of your graph, at the outside edges, and let's say the prediction from the edge to which is just a hyperparameter, differs significantly from what the whole graph thinks of that the belief should be, then you have a reason to extend your model, right?
Okay.
So this is, I mean, it's not we're not doing this in our toolbox yet, but this is one way, I think, where we can go to do structural adaptation under the drive of free energy minimization.
Oh, that's fascinating. Can you talk more about that?
Well, we are. We are mainly interested in the realization of active inference in my group, right? So when I said, I'm not a philosopher, by that I mean we don't talk a lot about what philosophers talk about. We just want to make it work, right? What we talked about earlier. We are interested in making it work. It turns out it's actually very hard to make an active inference agent work in the field. I think it's reasonably doable to make an active inference agent work as a demo, right? Because then you don't have the real world constraints of, well, the world may change and you may have power budget issues. You have to divide your power budget on the spot, because new situations appear, but in the field, it's quite difficult. So our toolbox now is pretty good in state estimation and parameter updating in pretty much in real time, but structural adaptation is a real problem. I don't think anybody has, as a community, we haven't really tackled that, and it's just not just the active inference community. It's, just the whole engineering and science community doesn't have a good approach yet for online structural learning, right? And
let me just get in there for a moment. Like, give me an example of online structural learning that a human being might do. Like, what's a situation where a human being demonstrates that capability as an active agent?
Well, if you learn how to ride a bike, you don't need to read a meter of books, right? You just go out and start riding a bike. Your model starts making predictions when you ride a bike. So also predictions for, let's say that you start riding and you start to fall. And I need to, what kind of actions can I take? Well, I can turn my handlebar. So what your model will do, because if you have a generative model, you can actually roll it forward in time, and you can roll out the different scenarios under the various actions you can take, namely how far do you turn your handlebar. In the beginning, your model is all wrong, so you're going to make big prediction errors.
Sure.
It's all wrong. These prediction errors get processed. They get processed by updating states. If they still persist, you will have to update your parameters. If they still persist, well, eventually you have to make updates to the structure of your model. Because in the end, an active inference agent is only interested in making good predictions. Right, so the first step is just to update your states, then to update your parameters. But in the long run, we're going to have to update our model. And if our model
Yeah, I was just going to say something interesting too about this situation is, so I'm trying to learn how to ride a bike. There's really a relatively small, at least in a qualitative sense, a relatively small number of things I can do, actions I can take, right? Like it's either I can move this arm or pedal this foot or that foot a little bit faster or harder. Like it's quite a manageable set of actions I can take, though they're continuous. So maybe there's a bit of, nuance to that. But it's interesting that the model is I hate to say compressed again, but it's compressed through this filter of a very small number of actions that it can actually take in the world, right?
Well, I'm not so sure if that's really the case, because you can also move your body on the bike, and you can move your point of gravity, and your point of gravity will affect how much you will need to turn your handlebars. So it's very complex relationship between the position of your body, how big the bike is with the slope of the street, and the speed that you're taking, and how far you have to move the handlebars. So it's just this whole physics.
It's complex, and it's nonlinear.
It's
very
nonlinear,
complicated,
and
nonlinear.
It's very situational, right? It's very. I mean, it depends on the particular bike you're riding and the particular road that you're riding on, the slope, everything. So generally, once you know how to ride a bike, you can make these adaptations pretty quickly. But if you have to learn it from scratch, you may have to do some. I mean, it may take a few weeks, because you may have to do at least some serious parameter updating, and perhaps even some structural updating, right?
Interesting.
Once that works, though, and your predictions are all correct, I mean, then you can ride your bike without even thinking about it, right? It doesn't, because your predictions are correct, means that you're almost generating, your prediction errors are very small, so there's no processing to be done, and so there's no computing power to be spent. The things that you learn to do well, the skills, over time, they will cost less or less and less energy in the brain, and that's also really good, right? In engineering, that's usually not the case. But once you learn...
So tell me why. I mean, because what are the biggest challenges to real-time, online, structured learning in the engineering case? Like in a sense, what's the magic trick that life forms can do that we haven't yet figured out how to do in silico, if you will?
The example that I like is the human body, and I'd say that tries to control is to be for homeostasis, right? Which is a control process that is beyond anything that engineers will ever build, right? I mean, we have 10 million sensory neurons processed by, 80 billion internal neurons, and then relayed to 50,000 muscle spindles. So it's beyond anything that we will ever build. Apparently, the brain does that just by variational free energy minimization on a computational budget of, maximum 20 watts, and it does it in real time. So we have here something that we can never, ever, we're not even close, right, with our control theory, with our machine learning, to build a control system like this. So the difficulty is to do interesting things. That means to minimize variational free energy on a low power budget in real time, and minimize variational free energy for the processes that matter. Right? It doesn't matter whether the car that I'm looking at, if he's blue or red, but it matters if he's coming in my direction or not. So spend your resources just at the stuff that matters, and be able to interrupt at any time for stuff that matters even more. Right? And this is quite different from what how most of us think about designing good algorithms in engineering. We just think about high accuracy, but not oh, I need to be able to interrupt it and switch to another process. I need to be able to do the same algorithm, but now on 30% of its power. Or I need to be able to do the same algorithm, but now the car that comes at me drives 120 kilometers an hour instead of 80. So I have a shorter deadline. So when all these constraints, the computational resources that you have in power, time, data, when that differs all the time, and you have a different environment around you, you still want to have a performing agent or even set of agents, and that means they need to be very robust. They need to work on 50% of the power as well. And they need also work if I have a smaller deadline. So that I think is where I see the most promise for active inference. We're not there yet. I think active inference is a fantastic future, but we're not there yet in implementing agents in such a distributed way and so always interruptible. For energy minimization over states, parameters, and when needed over structures, and stopping processes that are not important, right? So this is a big challenge, right? So and that's what, at least in my group, we try to focus on. Try to build a generic toolbox that would scale and that would do as much for energy minimization as we can, for a small power budget or for a small temporal budget. That's
really fascinating.
And I think that's also where this field differs from generative AI, because in a sense, active inference is also generative AI, but now it's generative AI in the field, right? It's the next, I think, wave of generative AI when we take these beautiful models, these diffusion models and all these models into the field. And now we have a power budget because they run on batteries. So do we. We also run on batteries, right? And and there are deadlines now, and that's very tough because the deadlines are not predictable, and the budget is not predictable, and so that requires a new computational approach. I think active inference is very promising in that respect because everything is variational for energy minimization. And you can implement it in very small units of time in a very distributed way. So from a computational perspective, it's just a path toward getting agents to survive in a world where everything can change on a limited power budget.
Mm-hmm.
Right? So I have no argument or complaint with generative AI. But we need to take it, if you take it into a field, you can easily create a world where it will fall apart. And this is the robustness that's currently not there. And I think active inference is hopefully is going to be a way to make that transition to situated agents.
Yeah, it's really fascinating. I mean, and everything you've been talking about, it seems to me the key is better methods and techniques to design and implement algorithms. It's not a case of like, well, we just need smaller CPUs and faster CPUs and maybe like some GPUs in there and stuff like that. It's not a hardware issue. Fundamentally, this is really an algorithmics issue. It's an algorithmic design issue. Is that correct?
I think so. Yes. I mean, it's a completely different approach to programming, right? It's a new concept, which also means that it's going to be hard to introduce this in the engineering community. I mean, we aren't even out of the discussion yet with, let's say, the control theory community about why don't you use a cost function or a reward function, right? I mean, this is a discussion that I think active inference community has very good answers for, but we haven't been able to convince the control community fully yet. On the other hand, now we need to implement it, and we need to talk to software engineers and hardware engineers. And we're going to have a similar mountain to overcome now, because we're saying we don't want to write these procedural algorithms. We want to write a self-organizing system, right? And that's going to be difficult,
And I mean, we were talking about this over lunch, but I think one shift over the next 5 years is we're moving towards this ecosystem view of software, which is that software is grown, it's not designed. And I think we're going to see all sorts of interesting scaling bottlenecks, because we basically have all of these agents that are diffusing information. But when I say diffusing, I mean sometimes they're not directly passing information, it's going over several time steps via other agents. So information is diffusing in the system, but there are weird bottlenecks. And as a developer now, it's really interesting as a developer, your life has just completely changed over the last few years. Now you're using language models, but soon you'll be like a neurosurgeon. So rather than just understanding how the software works, you'll just be looking at this thing. You'll be looking at these behaviors, and you'll be trying to swap out agents and try to, affect changes by poking the system rather than just directly changing it. So, I think it would be quite interesting how this pans out.
Yeah, and I think the scary part is going to be when we have to start talking about the psychology of our software systems, right? Let's try to understand the emergent behavior of our software systems.
But just on that, Keith, we are talking about emergence, right? We're talking about these very low-level, simple prediction models that give rise to extremely complex behavior. But I think a lot of the confusion when people talk about it, as you pointed out with the evolution example earlier, is that things happen at different scales of emergence. Yep. So I think, individual models I think of as being quite inflexible. But when you look at the process that generated the models, then it is flexible. So I think our mindset is changing with software, that we're starting to increasingly view things in a more abstract level.
Yeah. So I think there's going to be less algorithm writing, and more indeed, like talking about what is desired behavior of these things. So there are these nice pictures of a lightning strike with all the branches, right? If it's at the right moment. And these you can this is also energy neutralization, right? There's a big potential, and it's just neutralized over the earth. And so you can see this as tree search and cutting branches and everything. And I think that's also what's going on. But nobody designed that algorithm. Nobody wrote a depth first search, and then when this happens, I do this. Or there is no. That's just following the physics, and it follows the physics of we neutralize energy differences of any kind in least time. That's the physics, right? And how that unfolds, so it unfolds.
Yeah.
And this is the kind of software that we have to write, and so that's difficult because most of the reinforcement learning literature is about algorithms to search trees and to cut trees rather than software of autonomous nodes that kind of resolve it locally, right? That say, the prediction error is so small, we can stop here, guys. Nothing to see anymore.
This is a really interesting idea that we're talking about self-organizing software, which is very similar to Stephen Wolfram's Rule-Iad, which is this idea that you can think of the universe in a constructivist way. So lots of simple rules that over time construct to produce incredible complexity, or you can think of the universe as all of the things that could possibly happen, and you can kind of progressively remove it until you get to the universe that we live in now. But we were talking about algorithms, and in deep learning, you get this weird hybrid. You have Monte Carlo tree search, or you have tree of thought, which is basically an A-star search. And there's always explicit kind of planning algorithms built on the top of, even with a language model, how do we traverse the all of these tokens, it's a beam search. And I would imagine, but you corrected me earlier, I would have imagined that even in a multi-agent active inference setup, you would do some kind of a beam search against some kind of planning function in order to select the best trajectory. But you're kind of saying that's not the case?
No, I think it's not the case. Yeah, I think we shouldn't try to write these tree search algorithms.
Yeah.
I think this the thing is that even in the case of, let's say, this lightning strike, it goes around. It tries a branch. It's an explorative branch, but it ionizes the field around it that affects.
Yes. Yes.
The thing is, an agent affects its environment that affects the agent, and so forth. So you get in this loop. You just have to let it unfold until there's no more opportunity to minimize free energy, and then stops.
But so this is really interesting because there's this Chinese room argument, and people say John Searle in the room doesn't actually understand. And what you're saying is that we should get to a point where no individual agent actually plans. And but the planning is diffused, so the planning is in the system, because even if the individual bits only did what they were supposed to do in the moment, my take on Friston is that he's saying that they do develop this kind of temporal planning capability.
It looks like that.
Yeah,
but I think look, there's one thing in active inference and also in reinforcement learning. You say, well, I want to attain a certain state in the future, right? Whether you do it by a reward function or by some constraint on a probability distribution, you say we have these states in the future, and we're going to constrain them in some way, and now I'm going to predict. And kind of refer and then work backwards. What kind of action should I take now to up the chances that I will get in that state?
Yes.
The impression that I get from the literature is that people always start with saying, okay, we go capital T, that's our horizon, right? Or then we go predict, we collect that reward, and we go back. As if it starts with setting the horizon and then the prediction, collecting the reward or measuring the reward. I think it's the other way around. You shouldn't set a horizon. There's not. Why should you predict the future if there's no information there? You should just wait until some other agent on some other set of nodes says, "I have some information about these states." Mm-hmm. Right, you should keep your feet off the ground if you want to ride a bike in the future. So, then that will instigate some message passing there, because now there is an opportunity for free energy minimization. It's not, but nobody sets the horizon. It's just the process that happens to put some information there.
Yeah, and I guess that's what I mean by the diffusion of planning.
Yes.
Yeah. So it's fascinating, isn't it?
It's really fascinating, and I think you can actually, we know this in computer science because, for example, think of all the algorithms that are divide and conquer, right? Like the idea is I'm trying to look for some global solution, and the way I should do that is to divide it up into a bunch of subproblems and then solve those, and then divide those up recursively into subproblems. So dynamic programming, quicksort, all these things. And so the idea is I can just keep repeating this little simple algorithm at the very bottom and then get a solution and go up to the next level and the next level and the next level. And in a way, that's what we're talking about here, which is what type of kind of simple set of rules can you put into an ant so that if you take 5,000 ants, you get a colony, and it's doing this kind of interesting stuff, right?
Yeah. And I think that's, so in the end, then almost at every level that you look at, every layer or every node, you always say, well, this system is just trying to predict its world, and it gets corrected by sensory inputs, whether they come from a lower layer or from other nodes or from sensors. It makes predictions, gets prediction errors, they get processed. That's it. There's nothing else going on.
Yeah.
Right. There's one twist, and it is that there is encoded a certain goal of staying alive or what is success, setting constraints, and that makes this active inference loop not an objective, let's say, scientific inquiry loop, but it makes it an automated engineer. It makes it an engineering loop. Because now there is a purpose to it.
An automated engineer. I like that.
No, but really, right? I mean, the actions are the if there wouldn't be constraints, then you would just have you would build a model of the world in an almost optimal way, right? You make your actions; those are your trials, and you get your sensory observations, right? And you process them both in an optimal way. But because of the constraint, there is a bias, and now it has a purpose. It's still doing the objectively best process, the Bayesian process, but now with this constraint, it turns into a purpose. It turns into a vacuum cleaner or, whatever it is, a drone. So active inference to me is an automated engineering process, which is why we can develop with our brains speech recognition algorithms and object recognitions and navigation algorithms and locomotion and all these things. They have a purpose. So the brain is an automated engineer now through an active inference loop.
And I've often sort of thought that the only and I first started thinking about that. I was working at IBM for a little while, and it was at the time when they were developing the blue things like Deep Blue and Blue Gene and all these kind of supercomputers. And one day I was chatting with some of the engineers there, and they were talking about, as they scaled to larger and larger systems, for every single CPU they added to do something useful, they had to add a CPU to handle the communication of that CPU to like other CPUs, right? And then then they needed a CPU for that guy. And so there was this kind of, it became very difficult to scale monolithic sort of structures, and so the only truly kind of infinitely scalable control is distributed control of exactly the kind that we're talking about, where you kind of push out control as far down to the bottom layer of the tree, if you will, as you can, and then let kind of these larger scale control systems self-assemble or emerge from these distributed control programs. And so I have a tremendous amount of sympathy, for this approach. I'd like to see it applied even more broadly, like to say, I don't know, political structures. Like maybe we should distribute the control a bit more and like not keep trying to create, more and more control that's top heavy, right? Because it just doesn't scale. It doesn't produce optimal results. It's not flexible. It's not adaptable.
I mean, could we touch on another couple of things? Because what you were saying there is very interesting, Keith, and earlier on we touched on this notion of a scaling bottleneck or an information sharing bottleneck. And when we were in the car as well, we were talking about the robustness of the real world is because we don't explicitly program in purposes. And this stack of intermediate sub-goals, they are learned. Because when we build active inference systems, we need to start by handcrafting almost the entire stack. The goals, the sub-goals, we bias the system. And then when we have something that works, it's an agent-based framework, so it'll still be significantly more robust than this monolithic approach that Keith was talking about. But eventually we want to start introducing variance. We want to remove the biases. And I was thinking that one of the reasons that the natural world is so robust is because the agents are themselves nested. Everything is seeded from the microscopic scale. So even we as agents are composed of a hierarchy of sub-agents. And in the artificial setting, as I just said, we fix a whole load of the goals and layers, but the agents are also atomic. So how do all of these things affect things like scaling bottlenecks, resilience, robustness?
I think, if I take that as let's say a factor graph approach, which is nothing but saying it's just a divide and conquer approach, right? So you have a factorized model, and each all the processing is just factors, nodes, sending messages to other nodes, to connected nodes. That's the only processing that's going on. you can do in that node whatever you want, as long as the API is good. As long as the other nodes thinks you are a regular node in a vector graph, it's fine. We are currently experimenting with putting Gaussian processes in those nodes. I mean, they are non-parametric models. They're very different from the parametric models. But nobody knows that in the graph, because as long as on the outside, it just looks like a vector node. You know, if it quacks like a duck and it walks like a duck.
Yes.
Right. So
Can
that's
even be a subgraph.
yeah. So that's one thing. The other thing is, of course, that so if you do this in a reactive way and you don't have a preset schedule, then any schedule is you just follow the physics, right? So if you take out a node because you burn out a transistor, fine, it takes a different route. It's just a switch to a different model. So in a sense, structural adaptation is the other side of the same coin as robustness, because burning out an edge or a node is also a structural adaptation, right?
Yeah.
And so.
So there's a diffusion of function, and there's a clear information architecture. There's an interface. I mean, in Versus, for example, they've got this spatial, kind of schema, for want of a better word. So there's a clear interface. So I can see how that gives you a lot of resiliency. By the way, we haven't talked about kernels in over 2 years on MLST. You just peaked when you're talking about Gaussian processes. It just made me realize that we're so far away from our early roots in machine learning. But
we'll wander back there.
We'll wander
back there eventually. Yeah. So I think there's kind of two things I'd like to hit on before we leave. And one is, I'm always ranting about this, that there are no silver bullets. Okay, like everything, no free lunch theorem, no silver bullets, like that sort of thing. So back at the beginning, we talked about, Bayesian methods tell you have to do this impossible integral, which we can't do. And so we have this variational message passing, which is one framework that can give us efficient solutions, but there has to be a trade-off. And I know that part of the trade-off is there are certain models that work well, like in a variational message passing. Like traditionally, it's models that are conjugate. These are things that have forms, let's say, just for the listeners, similar to Gaussians. You just mentioned, Gaussian mixture models and things like that. Typically, they work better with linear systems versus nonlinear. But I know that a lot of your research has been kind of expanding that frontier, like finding kind of clever, tricks and clever heuristics to make variational message passing work with larger and larger classes of models. Like, can you talk about, where are we at today? Where's kind of the state of the art of how broad the categories of models we can handle are? And if you could find a trick tomorrow to add one extra, class of models that we can't currently do, what class of models would you choose to kind of slip in there?
The toolbox that we are working on, it's called RXInfer. RX stands for reactive extensions, and infer, dot ML, machine learning. So it's a toolbox for variational free energy minimization in probabilistic models. That's it, and it can of course be applied to active inference. It doesn't have to be applied in that context, right? At the moment, we are pretty good in, let's say, doing message passing in almost everything that relates to the exponential family of distributions, which are most distributions that people have heard of, right? Like Bernoulli distributions and Gaussians and Gamma and Wishart and all these distributions. That works very well. You can also put nonlinearities, deterministic nonlinearities in between those factors with nonlinearities, like a logarithm or an exponent or a sigmoid. If you put these together, you have already a very large set of models, right? So we can do a pretty large set of models, and not everything works as accurate as not everything works in the same kind of accuracy, because if you go through nonlinearities, you have to make more adaptations, and we also want to do it fast. So there are trade-offs that we're working on. In the end, what we want to do is make a toolbox where the inference is automated. Because in non-trivial models, you cannot derive it anymore by hand, right? So we want to have people come up with a generative model. Well, what's that? Half a page of code. That's not much. And then you say, you hook it up to your sensors and actuators, and you push a button and you say optimize for speed or optimize for time or for accuracy.
Yes.
Right? And if you say optimize for speed, then we take the fast way. It's gonna cost you a bit of accuracy. If you say optimize for accuracy, well, we may do some sampling even in between, just to get in there. Ideally, if you are in the field with your agent, the agent should even make that decision, and it should be context dependent, right? Yeah. So there is a path that we want to take to letting the agent, so that the engineer will just have to worry about the model, and no longer think about the inference. That should, because it's too hard for engineers to actually derive the right algorithm when the world changes. It's also hard to educate people during a master's program to become really good at variational free energy minimization in the real world. And if we want, one of the successes, of course, of deep learning is that every graduate student can now design a solution with a deep neural network. If we want active inference to have an impact and go to situated agents, then it must be democratized. We must have graduate students implementing these agents. So I'm happy to teach them about generative models, but I'm not so happy to teach them about how to manually derive inference in these models. And even so there's a limitation. I'm also not so sure if we should focus on building an even bigger model scope, because that was your original question. Okay. What would be the next model to be? I'm not sure if we should focus on bigger model scope, or let's start building agents and let the world tell us what works and not, because we may already be there, and we would be building all kinds of machinery for models that we don't need, right?
Yes. Okay. I mean, just a quick clarifying question. So there have been probabilistic programming libraries for a long time. I played around with one called infer.net, which was by Microsoft Research Cambridge. I think Thomas Minker's team was developing that. And that had a lot of the same kind of stuff, so approximate inference with variational message passing and so on. So people were using that just to do generic probabilistic programming. And we're talking about this active inference framework. When does the probabilistic programming stop, and when does active inference start, and when does the agent framework start? Do you see what I mean? There's this kind of like little ladder that we need to climb up.
In a way, I think writing software for an active inference agent is probabilistic programming. Right? Yeah. I mean, whenever you have variables and you don't assign values, but you assign probability distributions, and you want to calculate how these probability distributions propagate through your model, you're doing probabilistic programming, right? Yeah. Infer.net, of course, was the success of Infer.net on various large problems was quite a motivation for us. But we for active inference, it's all about going into the field. So it's all about doing free energy minimization or message passing under power constraints, under deadlines, temporal constraints, data constraints, missing observations, nodes that burn out, and still have keep everything working, right? That's I think where we want to differ with our work. It's not done, right? I mean, this is a long-term project. So more generally, I think active inference is is a really new field. There's a fantastic future, but the implementation is something that people haven't really thought about yet very deeply, and the implementation is not very simple. So that may be we need a lot more research to get this really working. I mean, deployable agents that really adapt in the way that we want to, right? I mean, yeah.
Yeah, and even with them. Sorry, Keith.
I was just going to say, I'm just curious. Are you finding it difficult? You know, because you're a professor, and so you're trying to educate your students, and you want to do right by them. So you want to try and teach them about active inference because you believe that it's a a tool for the future. I'm just curious if you're running into much resistance in I don't know, getting people interested in it, or teaching it, or getting funding for projects, related to active inference. Do you see a lot of resistance, or do you see open-mindedness?
Both, but certainly a lot of I wouldn't say a sort of a resistance, but not ill-willed resistance, just skepticism, right?
Skepticism.
Yeah,
okay.
And so it's very hard to attract good students because there are much easier ways to get a master's degree than with Butch, and you can get a much easier result with a deep neural net if the world doesn't change. Right, and if you don't have let's say a power budget, then I think you should use a deep neural net. It's fine, but so in the choices we made them like 8 years ago was okay. We're going to do active inference that nobody understands. We're going to implement it with factor graphs that nobody really knows about. We're going to program it in Julia instead of Python because Julia is fast and Python is not. And then we're going to do it in a reactive programming style. So,
oh dear.
So a niche within a niche within a niche. Huh?
A niche within a niche within a niche.
Full
yeah.
niche.
So, but it is of course a problem then to get a student and get him even started, right?
I think even then though, so reactive programming is a phenomenon that's taken off in many different languages. But I guess what I'm saying is that if you're a grad student in your early 20s, picking up a new language isn't going to be a problem. I think I always felt when I played around with probabilistic programming that the bottleneck was the modeling and also just all of the kind of the general knowledge you need around, you need to know about Bayesianism and factor graphs, and it's just not easy.
No. But I mean, the long-term impact on engineering could be enormous, right? In academia, for instance, because active inference says, hey, a control system, that's just prediction and error correction. Speech processing is prediction and error correction. Computer vision is prediction and error correction. So all these different disciplines are sort of have now a new approach, and we could even make a good case of why it's a very good approach. Now, so I would advise students, go in this direction, but it's not an easy direction.
Just the difficulty. I mean, let me ask you this question, which is, I would think that as the world increasingly relies on embedded devices, low power devices, Internet of Things, as it becomes more almost electronified in a distributed way, like more and more things become, digital systems, your thermostat, your smart home, like cameras over here, or whatever. Like this has to help at least put some pressure to embrace active inference, because that's its natural, swimming plane, right? Is or not?
Yeah, I think so. I mean, I think blockchain also, right? Blockchain is a distributed ledgers. I heard the other day the CTO of Algorand say, Algorand is really just a distributed operating system, right? And I'm not sure if you can run distributed active inference agents on algorithms, so don't know really anything about it. But there is, of course, there is a tendency to, or there is quite some research going on in making systems more distributed, and it will have an impact on robustness, on power consumption, on shared and emerging intelligence. So
yeah. But could we tease apart, because I'm very excited about distributed systems, and also if they are agent frameworks, that's very exciting to me. But what is the cash value exactly of the active inference over just any distributed? I mean, for example, you could have an agent framework where we have agents that are using OpenAI's new language model bots that they.
I think it's the fact
released.
that all the processing is variational free energy minimization. There's no other process going on, and variational free energy minimization can be executed in a distributed way, so parallel distributed, and also also through message passing and colliding messages in very minor or very small time instance, which means it's always interruptible. You can just cut a process short. You have a less accurate result, but you have a result. If I do some depth first search and I cut it halfway, I'm not even there yet. It's right. So you can't. You need a process that it's doing doing free energy minimization on a global scale, but it's also doing it locally, spatially locally, at any node and at any small unit of time, and so it can be cut and morphed in all the ways that the world can change.
Yeah, so something you were just saying is a very, very similar concept, I think, to this notion of subsymbolic. So subsymbolic is this idea that your knowledge and computation is diffused over many nodes, and that's neural network connectionist people always said subsymbolic systems are great because we have this kind of diffusion. And then Karpathy came along and said, well, yes, it's software 2.0. You can now sparsify the network. You can delete half of the connections, and it still does the thing you want it to do, just not quite as well as before. So that seems like quite a related concept to what you're saying about the diffusion of processes in a system.
Yeah, and with the side remark that if you go out in the field and you have a changing world around you, that you're forced to do these prunings and forced to cut short and forced to say, no, you just get 1 watt instead of 2 watt now, and a moment later you get 2 watts. So you're forced to you have all these fluctuating computational resources, and so it's true. The neural net works when, let's say, when you take out half the connections, but we're dealing with a situation where the number of connections fluctuates continuously.
Yes.
Right, or at least the effective connections fluctuate continuously, because we're forced to. That's the best way to go.
But are you making the argument of robustness, which is that you can remove some of the things and the process won't be affected? Or are you making the argument that what the process is doing is kind of not only diffused over the entire system, but progressively computed, which means it gives you as an engineer more flexibility to say, actually, I'm going to remove half of the nodes, or I'm going to stop processing now, and I've still got something useful?
Well, so let me jump in, because the way I look at this, and tell me if this is wrong, Bert, is I think about the old school, GIFs that used to progressively come into focus on the web, right? So you would go to a web page back when things were really slow, and you would get kind of this low resolution vision of the image, and then the resolution would kind of double and then double, and after a bit it would be the full resolution. And I think the point is, I could have stopped it at any point along that chain and had like a decent image, right?
Yeah, that's exactly
it. It wouldn't be high resolution.
Yeah, that's exactly it, right? And it's just, you don't have to. So it's okay if you have all the computational power in the world, it's you can track this car very accurately, and you can do so because you have a lot of computation. But in the end, if your computational power shrinks, you just want to miss that car, right? That's the only thing you care about. So you don't care about if it's a beautiful car or where its headlights are. You just want to miss it, right? So the amount of computation you do, you want to scale it down, and indeed at the resolution that is just needed to not hit that car, right? That's the only that's
Right.
the highest resolution that you need, ultimately.
Right.
Yeah.
Yeah, and the other thing too is, and this is kind of a minor point, but it's one that is important, I think, and should be realized, is that, because you mentioned the depth first search, when you go to run a prediction or a score, let's say on, a neural network, okay, it has to perform every single one of its layer steps in order to get the result. If you halt it at any intermediate step there, you have no result. You just have a bunch of, more or less meaningless bits that haven't yet been combined. Now that, like today, that may not be a big deal because maybe still neural networks only have some dozens of layers or something. But at some point, if you've got very, very deep neural networks, that inability to stop it at any point along the phase means that the entire computation is either completed and worth something or just worthless and got halted,
Yeah, exactly, right. So you want a process that is always interruptible, and that also runs when the computational resources fluctuate, right?
Well, that too, yeah. So you may be able to take out half the connections or something. Can you take out half the layers?
And can you take out half the data, right? If I'm driving and I see a guy coming at me with his car, but I also see in the rear view mirror a car behind me that's speeding up, I may say, okay, I'm going to just check every 2 seconds in this rear view mirror, and that means I'm going to get less data from the car in front of me. So we're also trading off how much sampling do I do in the world, right? So there's data fluctuations, there's deadline or temporal fluctuations, and there's power fluctuations, all the computational resources. And that's the I think where the research needs to go if we're talking about getting to really robust situated active inference agents, right?
Yeah, it's so fascinating. It's very similar to what Michael Levin talks about in terms of morphogenesis and the robustness of biological agents. For example, they can self-heal. And you're talking about...
Is that the cellular automata that self-heal, like the salamander and whatnot?
That's a great example of, kind of morphogenesis in a CNN. Yeah,
so cool.
Yeah, I mean, I talk about it all the time, so I'm not going to bore the listeners with it yet again. But but no, this idea that systems can be robust, and I've never really heard people speak about this before. But you're saying robust in terms of where I sample the data, the time resolution, and even the data resolution. So being resilient to all of those things, and power. Yeah. And in order for you to be resilient to all those different dimensions, there has to be some kind of a diffusion of how that processing is done in respect of those dimensions. And that's, if you look at any software engineering systems today, that's just not the case, right? If you change any of those things, it'll just break.
Yeah.
And I think
it's like the ultimate divide and conquer. Like you're
exactly
dividing up on every single dimension.
So, and it's also, I think, when we talk about, okay, what is the killer app for active inference agents? Because I mean, it's not going to really fly with the control community until we have until active inference also has a killer app, right? And it would be one of those things where you scale down or you have a very limited amount of resources, and you just throw over your world. So it has to start up all these Kalman filters, and then I think you will see that an active inference agents, more gracefully can or will be more robust to messing up the world, right?
Yes.
So at least that's the goal. If we can do that with our toolbox or other people with a toolbox, if we can come up with a toolbox that does that, then I think active inference agents have a very good future.
Yes.
So let me throw out a crazy idea, and just tell me if I'm totally wrong. But what I think you're saying is that if suppose we figure this out and we have active inference and we know how to build active inference agents that can learn to do a very broad range of tasks. Could I, for example, take an active inference agent, hook it up to a car, let it learn how to self-drive a car, and once it gets pretty good at that, I now take it and maybe I throw it into an airplane, and it's actually able to learn how to fly the airplane kind of reasonably well pretty quickly, just having learned how to drive a car. Like, is that the type of robustness of kind of system we're talking about?
I think there's. I wouldn't do that as a first experiment, but
well, no, of course,
no. But in principle, of course, there's a lot of skills that are transferable, right? I mean, I also talked to Tim about that. There is this experiment with a ferret. They take the optic nerve and they hook it up to through the thalamus to the auditory cortex, and then the ferret starts to see again, because the auditory cortex will just start to serve as a visual cortex, because the cortex is just a prediction engine. It doesn't really know whether it's busy with auditory data or with acoustic data or visual data. It's just data that tries to predict. And in that sense, I think a lot what you learn while driving a car, it will also transfer to what you need to know when you drive an airplane, or probably better yet, let's say a moped or something, right? It's the same kind of traffic. So that will transfer quite well. Yeah.
Yeah, we were talking about this earlier, Keith, but Jeff Hawkins has this idea that these pyramidal neurons in the prefrontal cortex, they all basically look the same, and they're all connected to different sensory motor circuits. He said there was about 150,000 mini columnar units. But anyway, the point is that they're all the same, and they can be specialized for language or basically anything. But to me, that says, because you said they don't know about seeing or driving, but I would argue this is a great example of the externalization of cognitive processes. The knowledge isn't in the brain cells. The knowledge is in your eyeballs, in the way the roads are structured, the signs, all of these external cognitive processes. All the signals come into your brain, and then a map is created, a simulacrum of the outside world. And then we look at the brain and we say that's the knowledge, but it's not. It's just a representation of the situation I'm in.
Yeah. That's true.
And that kind of explains why you could connect it to any set of neurons and they would just take on the same specialization.
Yeah, we walk about, every day we have new situations, and we go through it effortlessly, right?
Yeah.
So,
Well, are there any other big topics that you want to cover? If not, I have just a personal fun question at the end here.
There is, this thing that I think of what the impact could be for, let's say, for engineers and designing algorithms in the future, right? Nowadays, when you have to design a hearing aid algorithm, because I happen to know about that, but it's very general. If you have to hire engineers for all the modules, for noise reduction, for feedback cancellation, etc. And then when you print all the code out, you have 40, 50 pages of code, right? And then half the team leaves for better jobs or whatever. And so over time, nobody really knows the whole code base anymore.
Technical debt.
Right. In the future, if these agents start to work, an engineer would write a generative model, which is half a page of code, or maximum a page. And then you would press a button. You say, do variational free energy minimization. And yes, that's still, the toolbox is still 50 pages of code. But it's variational free energy minimization is the same for robotics as for hearing aids, as for it's just logic, it's just probability theory. So you have completely separated your problem definition in your generative model from the process of proper reasoning about your problem, right?
So on that, very interesting. Now, there is in a software development project, there is a shared understanding of what the code does, and that understanding is diffused in the brains of the developers.
Yeah.
So no one developer has a complete understanding. God knows Keith always tells me when I break some of his code that I failed to understand something, and vice versa. And even more so, a lot of the code is generated by GPT models, which only further diffuses, degrades these shared understanding.
Not the code I write. I'm sorry, not the code I write.
I mean, Doug, I would never admit to it anyway. But no. Anyway, like no one, in a large project, the understanding is actually not very high. But you're talking about this new modality where we kind of train. It's a little bit like training a dog. That we optimize certain behaviors, and we kind of like say we want more of that, we want less of that, and we don't understand how a dog's brain works. I guess, is there a kind of chauvinism for striving to understand what the code does?
Can you explain what you mean by chauvinism?
Well, by chauvinism, I mean like we think that we are good software engineers if we completely understand how all of the code works, and maybe on any reasonably sized software project that's impossible.
Okay, I understand. So you're saying a software engineer perhaps doesn't need to understand everything of the code. I think that's true. I mean, most companies work perfectly well with not every software engineer understanding all of the code base. But the main thing is that you can now design a system, an agent, where your proprietary code for your company is this one page of code, and you can even go to the CEO and say, look, this is how we define the generative model of our vacuum cleaner, and we just license some toolbox that does free energy minimization, and there's people there are other companies that do that, and it has nothing to do with vacuum cleaning, but we need it, so we just license it. But it's much easier to maintain that one page of code, that generative model, that and file a patent for it, if you will. But you need a much smaller group of engineers to start up a company and develop a product.
Yeah. Okay. Because it's kind of related to, like with deep learning, the model doesn't have any value. It's you train it on data, and then the behavior emerges. But you're talking about this middle way where you could have a domain-specific model, which is a generative model, and it would work almost out of the box or with minimal training, and it would adapt and personalize to the user's requirements.
The point is that a hearing aid company shouldn't need engineers that focus on variational free energy minimization. They should hire engineers that focus on what is a proper model, right? So we need to educate engineers for building generative models, but only a different set of engineers should specialize in let's make better toolboxes for variational free energy minimization. But it has nothing to do with hearing aids or with. And now we have to also put good algorithm engineers in hearing aid companies and in vacuum cleaner companies and everywhere, right? So it's more. It just makes the technical staff just leaner and more focused on the core business of the company.
One point though, Tim, about this kind of chauvinism for code. Me personally, I'm okay with the idea that I don't personally understand an entire code base, but what I do want is that every bit of code was understood by some human expert who designed that code. And I'll tell you why, because as good as neural networks are, and we've talked about this a lot on the show, like they're great at the bulk, at the average case, at what's been sampled well. They're terrible when it comes to the corner cases, right? And so, for example, when some, AlphaFold, right, was heralded as the greatest thing that AI has ever done, we've solved the protein folding problem because we get 93%, 95% kind of accuracy on the structure and everything. Here's the problem though. sometimes 99% is not enough, right? And I'll give you an example. The James Webb Telescope, right? This brilliant achievement. NASA put this awesome new telescope 1 million miles from Earth. Okay, it's bringing back all this awesome data. That mission is said to have had 344 single points of failure. If any one of those 344 things failed, the mission, right, fails. Okay, if you want to have even money, like a 50% chance of getting the satellite up there successfully, of a mission success, every single one of those steps has to have a 3 nines success rate, 99.9% chance of success. If you want a 99% chance that the mission succeeds, okay, you need 1 in 30,000 chance of failure at every single step. This is not machine learning, folks. Like GPT's even been getting worse at basic arithmetic lately. Like we do have this expectation in a lot of engineering domains of 100% accuracy or 5 nines of accuracy, and we're just not there yet with neural networks, right?
Yeah. Could I quickly touch on that? I mean, I don't think understanding in a code base is even a binary, because again, there's a non-stationary environment, which is to say the same piece of code run next week will behave differently because the situations change. So in order to completely understand a piece of code, you would also need to understand the semantics of all of the libraries that it's using and all of the libraries that those libraries are using and so on. And it's just not possible. So we have a kind of reference frame, and then we do behavioral testing. We do unit tests and stuff like that. But I just think that it's something that we delude ourselves that we have when we actually don't have. And then we get into this modeling thing. So now we're talking about, okay, well, let's build a generative model. And we always have this question of, do I understand the domain enough to build such a model? And does it make sense to take a very complicated system and to reify it into, because a model is a projection. There is no Platonic model of anything. And how brittle would that model be?
Yeah, I mean, this is where we are with active inference, right? So far, people have been pretty bad about coming up with great models, right? And it used to be quite siloed. Like in speech processing, everybody uses hidden Markov models, and in control theory, everybody uses state space models, and because it worked for their fields, and then deep learning just threw everything off the table. Active inference is at the stage where, okay, now we need to also come up with the right generative models. We know they're going to be nested models. Are they just going to be nested POM-DP kind of models, or I personally like actually in the generative AI field these diffusion models, right? So I think this is where we're at the moment. So what are the right generative models? Because if you have to come up with a very specialized generative model for each application, we've just shifted the problem now from algorithm design to generative model design. So hopefully, rather than in engineering, we can shift from very specific algorithm design to quite a generic generative model design. And then we have gained a lot, right? If we have generative models that work across modalities, generative models where it doesn't matter if the data is speech data or vision data or some other sensors, right? Yeah. But as long as they're nested and we have some kind of an online pruning algorithm that takes out nodes that it doesn't need, then I think then we have you've made the task for the engineer a lot easier, because he doesn't have to come up with a very specific solution for each problem.
So this is having a library of core knowledge, basically. Yeah.
Well, cool. Let me ask you my kind of personal question. So the question I'm going to ask you, and I'll answer it first, is if you remember when you first became a Bayesian. So for me, it was when I was struggling with an inference problem. I was collecting photons from a technology called 2-photon microscopy, and I had very few photons. Okay, like a sample would be like 30 or something like that. And I needed to measure the decay lifetime. And like, I'm out there reading papers, how many photons, do I need? In fact, I find one that literally said, how many photons do you need to measure lifetime? And they went through a bunch of, sort of statistical analysis, and the answer was 10,000. Okay. And I'm like, I don't have 10,000 photons. I have, 50, and I can see on a graph what the lifetime is. Why the heck can't statistics, tell me what the lifetime is? And I'm sitting in my office pondering this, and I hear an office mate of mine laughing. He's just chuckling. And I go over and I'm like, hey man, what's going on? What you laughing at? And he goes, oh, I'm just laughing at this book. And he's holding this book called Data Analysis, a Bayesian Tutorial by D.S. Sivia, right?
Yeah.
And he's laughing at this example of a Cauchy distribution, where if you're trying to estimate the peak and you're using the mean, you're never going to get the answer, because every sample that comes in will just jump the mean, all around, because the Cauchy distribution has an infinite, second moment. And yet there's this other procedure, maximum likelihood estimation using Bayesian analysis, and you get the answer, right? And I'm like, can I borrow this book? Like, I really need to see this book. Yeah, sure. I take it, I read the book, it changes my life, gives me a totally different perspective. Ever since then, I've been a Bayesian, and I've understood probability theory like much more deeply. So I'm just curious if there was a point in your career where you shifted from being, say, an orthodox statistician to a Bayesian, if you remember when it was.
Yeah, and actually, it's not very different from your path. In 2003, a few books came out. One was Edwin Jain's book, Probability Theory, and the other David Mackay's book. And so I bought both books because Edwin Jain's I had heard of. I wasn't doing Bayesian stuff, but it was also early internet, and I had heard that he was kind of he had a cult-like status in probability theory, because he would post these papers on the internet that would have a completely different view on probability theory. Yeah. And so I thought, okay, now I might as well just buy the book and get all these papers together. And I really loved that book. I never read it in full because it's just too thick and too big. But everywhere you read in this book, you learn something. The clarity of his mind is amazing, and he is feisty, and he's personal, and I liked that so much that it's almost like, you read the personality, so I loved that. And then so I started looking for other Bayesian books, and in I think the book from Sivia that you talk about came out in 2006 or something, and so I bought that book, and I read the introduction, and I read the preface, and it really struck a chord with me, because in the preface he said, I was a student and I did probability theory, and it was all about dice and coin flips, and it was beautiful, but it was just toys. And statistics that worked on real problems, but I couldn't understand anything of it. It just didn't make any sense. Arbitrary recipes. And there is a different solution. You can solve statistics just with probability theory, and that he did in this book. It's a beautiful little book. I still give it sometimes to students to convince them of the Bayesian method, because it's a short book. The first 5 chapters, just read the first 5 chapters, and you get a different view on statistical signal processing or whatever, actually, or just on science. So I resonated with what you say. It was also that little book by Sivia, and later with John Skilling, right? And and then the book that really
I agree with your book recommendations, by the way. So Edwin Jain's book, Probability Theory, the Logic of Probability Theory, the Logic of Science, right? Isn't that what it's called? It's so fun. You're right. He's feisty and entertaining.
Yeah, but the other book that really, taught me machine learning, Bayesian machine learning, was Bishop's book. I just saw you.
PRML. Yeah.
And because he showed that
cool.
everything we do in machine learning, you can do better with with the Bayesian approach.
Yeah, and didn't he pioneer all of the variational message passing?
Right, I mean,
because all the latter chapters of his book are about that.
Yeah, and
his team at M.Sc was working on that.
I think it's still the book that I use for my machine learning class. I love that book, the Chris Bishop's book. I think it's still one of the better books in machine learning.
I can't see it now. You said you saw it.
I thought I did.
I can't. My
Is
mind's
that
blank.
pattern recognition?
There you go. Yeah, PRML. Look at this.
Yeah. Pattern recognition and machine learning. Yeah. Well, there you have. That's a good book list for our listeners. So we got pattern recognition and machine learning by Bishop, right? Data analysis of Bayesian tutorial by D.S. Sivia, and probability theory: the logic of science by Edwin Jain. Awesome. And the original you mentioned earlier, I think it's a 1946 paper by Cox, on Cox's theorem.
Yeah,
that's a really cool paper to read if you can get a copy of it.
Right. But I should also say, I mean, lately I've been there's this theoretical physicist Ariel Katica at Albany University, and he's doing amazing work if you're interested in Bayesian machine learning, because he approaches physics really as an inferential science, as information physics, and so he has also a monograph that you can just download from his website. And during COVID, he actually taught online. So there's on YouTube, you also have all the classes. It's fantastic. Nice. It's really fantastic. Yeah.
Beautiful.
Well, listen, I really have appreciated you coming to talk with us. I think you and Tim have been having a lot of fun over there. So again, thank you, Bert, for coming to talk to us. It's been an absolute pleasure.
Well, thank you. The pleasure was totally mine. Thanks.
Thank you so much, Bert.